We're always hearing about advanced composites, these super strong, feather-light materials that are building everything from Formula One cars to the newest airliners. And one of their biggest selling points is that you can make these massive single-piece structures, which, well, that should make putting them together easier, right? But here's the twist, the paradox. Assembling these amazing materials is shockingly difficult, super time-consuming, and unbelievably expensive. And just take a look at this. It really puts it into perspective. The cost of the material itself and making the initial part, that's only half the story. The final assembly, all the trimming, drilling, and fastening can eat up to 50% of the total cost of a finished part. That's just a huge hidden chunk of the budget. So that leads us to the big question, the one we're here to answer. Why? Why on earth is a process that sounds as simple as putting pieces together so ridiculously complex and costly when you're dealing with composites? Well, let's find out. To get to the bottom of this, we're going to go on a little virtual factory tour. We're going to break it all down, step by step. We'll start with making the perfect cut, then dive into the high-stakes world of drilling without causing damage, check out the incredible art of fastening, and finally, look at the all-important final touches. First stop, making the perfect cut. So a composite part comes out of its mold, and it's got these rough, uneven edges. They need to be trimmed down to exact dimensions. But let me tell you, you can throw out everything you know about sawing a piece of wood or metal. This is a completely different ballgame. So here's the thing you have to understand. It's all about the material itself. A piece of metal is pretty much the same all the way through, right? It's ductile. When you cut it, the little metal chips that fly off actually carry away a ton of heat. But composites? They're the total opposite. You've got these incredibly strong, abrasive fibers, like carbon, just sitting in a much weaker, brittle resin that's a terrible conductor of heat. It just doesn't get rid of it. And because of that weird structure, you're walking through a minefield of potential disasters. If you use the wrong tool or just the wrong technique, you don't just get a sloppy edge. Oh no. You can cause delamination, where the layers literally start peeling apart. You can get tiny cracks, fibers getting ripped out, or even heat damage that ruins the resin. And with something like Kevlar, you get this annoying fuzzing effect instead of a clean cut. Any one of these things can seriously weaken the part. So how do you cut a material that absolutely hates being cut? Simple. You don't. You erode it away. The go-to solution in modern aerospace is the abrasive water jet. And we're not talking about your backyard power washer here. This is a razor-thin stream of water pressurized to over 40,000 psi, mixed with a super sharp abrasive grit. It literally blasts the material apart on a microscopic level. The way it works is both simple and kind of brilliant. You've got this super high-pressure water that goes into a mixing chamber. In there, it creates a vacuum that sucks in these tiny, sharp particles of garnet. Then, that whole mixture, the water and the grit, gets shot out of a tiny nozzle as this focused, high-speed slurry. It's so powerful, it just erodes the composite cleanly, with almost no physical force on the part, and most importantly, no heat. Problem solved. All right, on to our next station, drilling without damage. So our parts are neatly trimmed, now we need to drill a bunch of holes in them so we can fasten them together. Sounds easy enough, right? Wrong. In the world of composites, every single hole is a precision, high-stakes operation. And here's the heart of the problem. As a drill bit starts to enter the top of the composite, its sharp edges grab those top layers and create a peeling force. Think of it like a splinter on a piece of wood. Then, as the drill is about to punch through the other side, it creates a punching force that can just blow out the back surface. You can end up with a mess on both sides of the hole you just tried to make. And again, let's just compare that to metal for a second. With metal, a regular drill bit just peels away a nice, continuous chip. It's clean. But with a composite, that scene drill is basically punching its way through a stack of brittle poker chips. If you get it wrong, you're not just making a messy hole. You could be creating hidden damage inside the part that could cause it to fail later on. The only way to solve this is with some seriously specialized tools. There's no one-size-fits-all drill bit here. For carbon fiber, you might use a special dagger-style drill that shears the fibers cleanly. For something like aramid that loves to get fuzzy, you need a special C-shaped edge that actually pulls the fibers tight before slicing them. Each design is a custom-engineered solution for a very specific problem. But the shape of the drill is only half the battle. What it's made of is just as critical. See, carbon fiber is insanely abrasive. A standard high-speed steel drill bit, you'd be lucky to get 2 decent holes out of it before it's toast.
2. If you upgrade to a carbide drill, you can get over 50. But for the big-time automated production lines, they use drills tipped with polycrystalline diamond, or PCD. They cost a fortune, but one of them can drill thousands of perfect holes. It's the only way it makes economic sense. Okay, so we've cut our parts, we've drilled our perfect holes. Now for what might be the most critical step of all, the art of fastening. This is where all that insane precision we've been talking about really has to pay off, because how you hold these parts together is a complete science.
So before we can even think about what kind of bolt to use, we have to have a quick chemistry lesson. We need to talk about galvanic corrosion. Carbon fiber is conductive, and if you put it right next to a different metal, like aluminum, you basically create a tiny battery. And guess what happens? The aluminum starts to corrode and just wastes away. That is why you always see super expensive titanium or special stainless steel fasteners in carbon fiber structures. They have to be chemically compatible.
Now get a load of this number, 5/1000ths of an inch. That's thinner than a sheet of printer paper. If the gap between two composite parts you're joining is any bigger than that, you can't just tighten a bolt to pull them together. The bending force would literally crack the brittle resin around the hole. Instead, a technician has to precisely measure that gap and fill it with a custom-fit sliver of material called a shim. The level of precision is just mind-boggling. And the stakes for getting any of this wrong are absolutely huge. A joint can fail in a bunch of catastrophic ways. The fastener can tear out the side of the part, it can pull right through the hole, or the part can just snap in half. The only way a joint is designed to fail is in what's called bearing, where the hole just slowly stretches under an extreme load without ever breaking apart completely. Every single detail is designed to make sure that's exactly what happens.
So to get that perfect joint, engineers use these amazing little devices like the Hi-Loks fastener. It's a two-piece system. You stick the pin through the hole, and then you thread on this special collar. A tool holds the pin still while it tightens the collar. And here's the genius part. When it reaches the exact perfect torque, the top of that collar is designed to just shear right off. It's a foolproof way to get the exact same clamping force every single time. Another really cool one is the lock bolt. This one doesn't even use threads. The pin has grooves instead. You put the collar over the pin, and a special tool pulls on the pin to clamp the parts together. Then it swages, or basically squishes the collar material down into the pin's grooves. This creates an incredibly strong vibration-proof joint. And just like the Hi-Loks, the pin then breaks off at a precise tension, guaranteeing a perfect clamp up. We are so close to the finish line. Our parts are cut, drilled, and perfectly fastened, but we're not quite done. The final assembly stage is all about the critical finishing touches that are going to protect this structure and make sure it does its job for years or even decades. And this really comes down to two last vital steps. First, sealing. I mean, think about an airplane wing that's also a fuel tank. Every single joint, every seam, every fastener has to be meticulously sealed up with these flexible sealants to stop leaks. And second is paint, which is way more than just for looks. A special epoxy primer makes sure the paint sticks, and a tough polyurethane top coat protects the whole thing from UV rays, moisture, and chemicals. So, after all of that, the high-pressure water jets, the diamond-tipped drills, the self-breaking fasteners, we finally arrive at the real answer to the assembly paradox. The ultimate takeaway from all this complexity is this: the best, cheapest, and safest way to deal with assembly is to not do it at all. The entire philosophy of modern composite design is to design parts to be as big and as integrated as possible right from the very beginning. And that leaves us with one last, pretty fascinating question to think about. We've just seen the absolutely incredible technology we've invented just to join two pieces of composite material together. But as our materials and our manufacturing get even smarter, are we slowly heading toward a future where the best, most elegant assembly is no assembly at all?